We'll be looking at a question on transition elements today from the June 2022 paper. Before we start the question, I thought it'll be useful to show you this chart of all the colors of the transition metal ions, their solutions, their precipitates, their complexes. I'll put a link of this. I'm sure all of you, most of you have this chart, but if you don't, it's a great one because it gives you all the colors of the solutions, the precipitates, the complexes, and you need to learn this all off by heart. So very important, and I will be referring to this while we're answering the question. So I'll put a link to this if you don't have it in the description. Moving on to the question. What we got here, this is question 22 from the June 2022 paper, and it's on transition elements and complexes and ions. And the first question is asking about reactions of transition metal compounds, transition metal compounds, and it's talking about this compound here, ethane di-1,2-diamine. It's saying it's a bidentate ligand. The structure is given to you. It's a skeletal formula. And it says, why is ethane 1,2-diamine can act as a bidentate ligand? You see, in this bidentate ligand, you got two amine groups, and the nitrogens have a lone pair on them. These lone pairs are what form a special type of bond. And if you go back to the definition, what is meant by a ligand? A ligand is a molecule or ion, that donate a pair of electrons to form a coordinate. You didn't learn this word in year one, but in year one, you did learn dative, a dative covalent bond. What is a dative covalent bond? You've got a shared pair of electrons provided by one of the bonding atoms only. So a molecule that donates a pair of electrons to form a coordinate or a dative covalent bond. Now, this question is asking about a bidentate ligand. Bi means two. So you just insert the word two, a molecule that donates two pairs of electrons to form two coordinate bonds. The word is two. And this word dentate, you can relate it to the word, for example, teeth, dentures, or dentist. So it's two tooth biting onto the transition metal ion. Moving on. The iron 3 ion forms a complex with ion A with two ethane 1,2-diamine ligands and two chloride ligands. Complex ion A has a cis-trans stereoisomerism and also exists as optical isomers. What's the empirical formula first? You see the empirical formula is going to have one iron. It's going to have two chloride ions, as it says in the question, and it's going to have four carbon. Four carbon is going to have four nitrogen. And how many hydrogens will there be? 1, 2, 3, 4, 5, 6, 7, 8. 8 times 2 is 16 hydrogens. So a bit of a counting game here. Let's have a look at what the mass scheme says. C4H16, N4, and CO2. Yep, that's correct. Now, for drawing the complex ions, lots of precious marks in these drawings. You see, let's draw the cis-trans. You've got your ion complex. In total, it forms 6 coordinate bonds. Learn to draw these diagrams and learn to draw them neatly. These bonds are behind the page. The bold ones are in front of the page. In fact, let's draw all of these so it's easy to fill in afterwards. Draw them nice and neatly. And when you practice drawing them, you'll be able to draw them faster. You see the examiners, they are sleep deprived. The markers, sorry, those who are going to be marking you up, they're sleep deprived, and they have a fraction of a second to make a decision whether you've earned the mark or not. If your work is not presentable, it's going to make it increasingly difficult for them to award the marks. Class, let's draw the cis version first. So we've got our 2 bidentate ligands. Let's draw our NH2s. It's the nitrogen that forms the coordinate bond. And don't forget to put the hydrogens after. Actually, that bond should be on the nitrogen, H2. And then you got your chloride ions. And you see, this is a complex. So the charge, empirical formula with charge. I missed that out. Didn't read that. Charge should be a +1. Why is it a +1? Because the ion has a 3+ charge. The diamines are neutral. So you've got +3, -1, -1, which gives you +1. Say that again, +3, -1, -1. So this overall gives you a plus charge. I'm gonna, you could a lovely complex and miss the charge. So please be mindful of that. Let's draw the mirror image. So imagine there's an imaginary mirror here. So you got your chloride ions. Let's draw our bidentate ligands. These may seem difficult to draw, but with a bit of practice, you realize actually they're a lot easier to draw. Once you've got the structure of the complex, it's easier to draw. Now, you see when you've got the cis isomer, cis meaning together on the same side, the mirror image is the optical isomer. Trans means across. So let's keep one chloride there and let's put the other chloride opposite. And you just put in your bidentate ligands like so. And put in our charge. And ladies and gentlemen, you have your, I'll label this as well. This is your cis. This is your optical isomer of the cis. And then here you've got your trans isomer. Okay. Quick look at the mark scheme. That's absolutely fine. In the mark scheme, they just rotated that a little bit, one step that way, but it's still the same thing. Next question is asking, aqueous sodium hydroxide is added to an aqueous solution of iron 2 sulfate, a pale green precipitate forms, which turns brown when left to stand in air. Let's have a look at what's going on. You've got an iron 2 plus ion. It's reacting with sodium hydroxide. Let's have a look at that chart. You see in the chart, let's have a look at iron. Iron is here. You got the iron 2 plus. Is it 2 plus? Just go back. Iron 2, yeah, sorry. Iron 2. So you got that solution there. It's a pale green solution. Pale green solution. When you add sodium hydroxide, it gives you a dark green precipitate. And you see, upon standing, it turns into a brown precipitate, as shown here. And why does it form a brown precipitate? Because the oxidation number of iron goes from a +2 to a +3. And it gives you the iron 3 hydroxide, which is a brown precipitate. So we're going to be referring to this in the question. Right now, I'm in an equation for the formation of the pale green precipitate. This is Fe2 plus in the presence of hydroxide ions will give you iron 2 hydroxide. It's not asked for the state symbols because it tells you that a precipitate is formed. But if it did ask you for a state symbols, usually they do, you would write this. And just to balance, put a big 2 there. Lots of easy marks with equations like this. The next question, use the information below to explain why the pale green precipitate turns brown. Why? Left to stand in air. What is in air that supports the reaction? In air, we're looking at oxygen. So some exposure to oxygen. You see, in this question, what you've got these 2 redox systems. Why does it turn brown? It turns brown, first of all, because iron 3 hydroxide, brown precipitate, identifying what that precipitate is. How would you know that? Because you've learned the chart that I showed before. Brown precipitate is iron 3 hydroxide. How do you get from iron 2 hydroxide to iron 3 hydroxide? That happens because iron is oxidized. Yep. And now you see which of these 2 redox systems, which one is more positive? Which one is more positive? It's redox system 2. And remember the rule, the more positive the electrode potential of the redox system, the greater tendency it has to gain electrons. So it'll go in this direction. And the less positive one or the more negative one will lose electrons. Okay? So let's have a look. You've got iron 2 hydroxide. It's going to react with hydroxide ions. It's going to oxidize the iron and it loses an electron. Whilst oxygen is reacting with water and is gaining the electrons from the oxidation to give you hydroxide ions. And you've got your reaction happening there. And putting that into words, redox system 1 is more negative than redox system 2. A comparison, or you could say redox system 2 is more positive, any one of those, or reverse argument, worth a valid point. And as a result of this, the redox system 1, the equilibrium shifts to the left, and redox system 2 equilibrium shifts to the right. It's asked to construct an equation for the reaction which occurs. And so what we do, rather than just writing out the answer, let's a little bit break it down. You see the redox system 1 is flipped. So you've got Fe, let's use a different color pen. Fe, it's going to react with hydroxide ions. That will give you ion 3 hydroxide plus an electron. And redox system 2, you don't flip, you just write it as it is. O2 plus 2H2 plus 4 electrons to give you 4 hydroxide ions. You see, to give an overall equation, you need to balance the electrons. You need to balance the electrons. There's only 1 here, but there's 4 here. So to balance the electrons, we put a big 4 in front of all of them. And we then combine the arrows. We combine the arrows, and you take away the electrons on both sides. And you then just combine, you cancel the electrons and you combine. And you see also the 4 OHs cancel out as well. So you've got 4 iron 2 hydroxide plus O2 plus 2 H2, whoops, H2O, whoops, whoops. And goes on to produce iron 3 hydroxide. And that's it. That's your overall equation. Let me highlight that. This plus this plus this goes on to give you this. That's your overall equation, because the others cancel out. This is a 6-marker question, and it's the last part of this question. There's quite a lot going on. And if you were to see the question like this, the psychology of it would naturally, make you think, oh, there's too much to, chew on this. Let's have a read. Questions about copper and copper compounds. Experiment 1, hydrochloric acid is added to aqueous. This copper complex ion, a yellow-green solution forms. It forms a complex ion B. Experiment 2, copper metal is heated with concentrated sulfuric acid. A reaction takes place forming a pale blue solution. We'll come back to the color chart in a moment. You got this much of gas measured at RTP, and the mass of gas D is that. It says an excess of copper 2 oxide is heated with nitric acid. The resulting mixture is filtered. The filtrate is a blue solution. The filtrate is a blue solution. Aqueous potassium iodide is added to the blue solution. And a white precipitate F and a brown solution G forms. It wants us to determine B to G. Construct equations. Where's all the marks from? Equations, changes in oxidation number, and show you're working to do the calculations. So quite a fair bit. Let's do it one by one. You see in experiment 1, you've got hydrochloric acid reacting with a copper complex, which is surrounded by water ligands. Let's have a quick look at our chart. You see you got this, and we're going to react that with excess hydrochloric acid, and it goes on to give you a yellow solution. So you've got a ligand substitution taking place here. So let's write down the equation. Cu 6 ligands of water. You've got the charge. We're reacting this with chloride ions that have come from HCl. Ligand substitution takes place. You got 4 minus 1 chloride ions, which gives you an overall 2 minus charge. And the water ligands are substituted off. Yep. You got the equation there. So here, yellow-green solution form. This is your complex ion B. Experiment 2. A big copper metal is heated with concentrated sulfuric acid. And it's asking, you got your gas. Pale, okay. Copper metal is heated with concentrated sulfuric acid. A pale blue solution C forms. You see the pale blue solution is going to be your aqueous copper 2+ solution. So that's either going to be copper sulfate, or we could just write down the whole complex. This is your solution, C. Solution C. And you see, this a reaction takes place. This is what's formed, and you've got this gas. This gas D has 45 centimeters cubed. If we divide that by 24,000, that gives us the moles. You got the moles, and you've also got the mass. The mass is 0.12 grams. And we know that mass over moles, n number of moles, that will give you the MR of the compound. Normally it's mass over molar mass gives you moles, but we're working backwards. So let's work this out. 0.12 divided by 1.875 times 10 to the minus 3. This gives you exactly 64. Now you see 64, the closest gas it could give us from these type of reactions is sulfur dioxide, even though that's 64.1. It's the closest thing. So using this information, it tells us that you've got copper, metal, reacting with sulfuric acid, which goes on to give you copper sulfate solution, some sulfur dioxide, and there's probably going to be some water forming. And how would we balance this? We can try normal balancing rules, but because this is a redox reaction, I'm not going to take chances. This is 0 oxidation number. This is +2. Sulfur is +6 here, but it's +4 here. So it's a simple case. One is losing 2 electrons. One is losing 2 electrons. One is gaining 2 electrons. So we can put what's the oxidation number here? +6, +8. Yep. -2 is that. Balancing. Aha. In terms of electrons, these need to be a 1-to-1 ratio. Yep. But you see, we've got a second sulfuric acid, which will just not change in oxidation number, and the sulfate stays as a sulfate. And the second one gets reduced. So you've got that, and you put a big 2 there as well. And you have your balanced equation. So this B, C, I think this was gas D. Is it gas D? Yep, we've got our gas D here. Then you got experiment 3. Experiment 3. Here, copper is heated with dilute nitric acid. The resulting mixture is filtered. The filtrate is a blue solution. You see, with copper oxide, it's reacting with nitric acid, and it gives you a blue solution. Copper, nitrate, and some water. Now, your solution, your blue solution is going to be this. You see it's copper 2+ ions. Is a blue solution E, so let's call that E there. Now, this is an interesting part. You see potassium iodide ions are added. It gives you a white precipitate and a brown solution. A white precipitate and a brown solution. Look at this. There's key bits of information here. If we write down the ionic equation, you've got your Cu2+. When you react it with iodide ions, this is a reaction that you need to learn. This goes on to give you Cu I. Oxidation number goes from +2 to +1, and it forms some iodine, I2, which has an iodine oxidation number goes from -1 to 0. And to balance, we put a big 4 there, and a big 2s there. 2, 4, 2, 1. Yeah. So you've got this reaction. You need to learn this equation, because in this reaction, it forms iodine. which in turn further can be reacted with thiosulfate solution, and a redox titration can take place to determine how much iodine has been given off. This could be possible questions. This is a redox reaction because you're going from +2 oxidation number +2 to +1, and iodine is going from -1 to 0. And let's just check the mark scheme. That are all the points that have been covered. Oh, going back to the question, white precipitate, brown solution. White precipitate, brown solution. The iodine is the brown solution. Iodine in aqueous solution is a brown color, and the white precipitate is the copper 1 iodide, white precipitate. You need to learn these observations and colors and these equations to be able to answer it fully. That is the end of that, ladies and gentlemen. I will see you next time.